All right, so what are we going to talk about today? Well, yesterday we looked at vector functions and their graphs, so curves, and how to parameterize them or describe them. Parameterize is just a fancy way to, say, mathematically describe a curve. Today we're going to move on to limits. Remember, this course is about vector calculus and calculus of functions of several variables. So you'd think that we'd cross limits at some point, right? Now, you would have seen limits at school or first year university, or probably both. But with vector-valued functions, there's a few little twists. So that's what we're going to talk about today. And tomorrow we'll talk about derivatives and integrals. All right, now, the good thing about vector-valued functions of one variable is that you can do a lot of things in a so-called component-wise fashion. So you can see up here, if these functions are the so-called component vectors of my vector function R, then what we mean when we say the limit as t approaches some number, t sub naught, all we mean is just the limit of each component function. And that gives you a way of calculating the limit as well. Okay, so for a real simple example, of course, this limit exists provided each of these limits will exist. So as a real simple example, let's consider the following vector function of one variable here. Calculate the limit as t approaches 1. Okay, so if I just want to write it out in the sort of ordered triple notation, I'm just going to write it like that. Now the reason why I don't write out all the i's, j's and k's is because it actually takes longer. You've got to write I, j, k, underline them, put a tilde underneath them. I just usually do my calculations with these ordered triples, right? So this would be your f of t, this would be your g of t, and this would be your h of t. Sorry, YouTube. So let's take the limits. So it's just the limit of each of the components. So writing it out in the following way, again in the ordered triple notation, it's just a component-wise operation. Okay, you can move the limits inside the vector and into each component. So the limit of the first component is going to be 1, the second component is going to be 1, and the third component is going to be 1. Now you might think, well, so what? That's easy. Well, it is. It is easy, right? But let's just think a little bit about what we've produced. What's the significance of the answer here, or our limit? Well, the limit is a vector, okay? Most of the limits you've been dealing with at school, you're just, the limit is 2 or the limit is 0. For vector-valued functions, the limit is going to be a vector, provided, each of the limits exist. So that's something you haven't seen before. So that's a simple way of calculating limits of vector-valued functions. What about if we wanted to get a little bit more precise? Now, some of you may have seen this definition in first year, some of you may not. 1131 would be the place where you may have seen it. Although this is in a slightly different form because we've got vector-valued functions here. All right, so let's try to read it and understand what's going on. Suppose we have a vector function here with these functions as the coordinates, the coordinates, I guess. Let this boldface L be a vector. We say that the vector function R has a limit, vector L, as t approaches some number t naught, and write this, if for every positive number epsilon there exists, or we can construct a positive number delta such that if t is in this interval here, then the difference, I guess the magnitude of the difference between the vector valued function and its limit can be made as small as we want. So you may look at that and go, oh, it's too early for that, Chris. It's like, it's my first lecture. I had to travel 4 hours to get here, right? Let's just actually break this down and give this some meaning. Firstly, remember, what I'm going to do on the right-hand side is put these double lines to make sure that we know we're dealing with vectors. You may already see, oh, okay, there's a boldface R and a boldface L. Well, duh. Well, just to reinforce it, okay? What does this mean? Well, let's try to explain it in a geometric way that's much easier, hopefully, much easier to understand. All right. So now I'm just going to, well, firstly, let's think about what is this? If there are my component functions, what does this mean? Well, it's just the following. L3. Okay, that's an L sub 3 on the right-hand side. Now, you can see why the notation above is much easier to use, because you don't have to write out all those bits. Now, the L1, the L2, and the L3, you can just think of them as the components of L. So they'll just be numbers. Okay, so I'm still confused though. Well, what does that mean? Well, let me give you a picture that I hope will give you some insight into really what's going on with this. Now, I'm just going to do it in 2D, and I'll let you make the generalization, because the picture's a little bit easier to draw in 2D. That's the only reason I'm doing this. Okay. So we've got a curve, and in this case I'm going to draw this vector, position vector L, such that the tip of the vector touches the curve. Now, think these vector functions can be thought so basically a vector function R takes an interval or the real line and transforms it into some sort of curve, maybe a curly curve, something like that. So think of this as the domain of the vector function R. Okay, now, if I draw, and this is the important bit, if I draw any circle around this point here, okay, let's just say it has an arbitrary radius, let's say epsilon. What this definition basically says the following. If I draw any circle around this point, then by restricting the size of this interval, I can always make the curve, or the part of the curve associated with this interval, fit inside the circle. Let me say that again. If I draw the point on the right-hand side, then I can always find an interval or construct an interval centered about this T0 such that the curve will always lie within the circle I've drawn. And that works for every circle. That's what we mean when we say the limit of a vector valued function is equal to L. So you can think about, this being okay, so that t there might refer to, I don't know, some t point here or something like that. But the point is, for all t in this interval, the curve, the green curve, will stay within a corresponding circle. That's it. That's all it is. Okay? Now, it'll take you a little while to get used to that definition, and mostly we're interested in just computing limits rather than getting wound up with epsilons and deltas and things like this. You can also talk about left-handed and right-handed limits. So when t approaches, say, t0 from the right, and when t approaches t0 from the left. But I'll leave those for you to do. Okay? Here's a good challenge. Try to think about what it means for a right-handed limit to equal some vector L, and a left-handed limit for some of some vector function to equal, say, a vector L. I'll leave that with you. Let's actually do a problem and see how we go. All right. If a vector function is defined in this way, then formally prove. That's a important part of this question. Formally prove that the limit. Oh, guys, you can't sit. Just come down here. It's actually you can't sit in the aisle. Formally prove that the limit of this vector valued function is 0. Well, first of all, let's. Or you can just come down here if you want. Or is that too close? It's okay. Like, do we suspect it's true? The limit of t as t goes to 0, that's 0, 0. And t times sine t as t goes to 0, that's going to be 0. So we would expect it, our common sense tells us that, yes, the limit must be the 0 vector. But let's formally prove it. Okay? All right, so let's identify it. Here, our vector valued function is just t, just written in component form. Our t0 is 0, and our vector limit is the 0 vector. Okay, so let's identify. You can come in the front, man, if you want to. Just don't be shy. It's all right. Okay, so what do we need to do? Well, we essentially have to show that I guess this is true for our particular functions and limit and point. So how do we do it? Well, let's start. I'm actually going to start working with this and then simplify as much as I can. All right? All right, so it's t sine t minus 0, 0, 0. Now that's pretty easy to simplify. We've just got the 0 vector here, so we don't really need to do anything. But remember, we've got magnitude here. So we need to square each of the components, add them together, and take the square root. So the zeros aren't going to affect anything. Okay. Well, I've got a common factor of t, But look at the sine squared. I can do something with that. I know that sine squared is always going to be between 0 and 1. So now I'm at the point where what I'm trying to do is form some sort of inequality, right? Because I'm looking for some sort of inequality. I'm working with this at the moment, and I'm looking to form some sort of inequality. Okay? So sine squared, so I can do this. And now I can just simplify. I'm going to get root 3 times absolute t. Now, you might be thinking, hang on, what's going on? What we are trying to do is to simplify and get something like this. Okay, something involving this. Let me show you. If I just write this as that, then I actually have this. Now, how can I make this whole thing strictly less than any given epsilon? Well, all I need to do is make this small enough. Anybody know how small? Almost. Epsilon on root 3, that's it. So let me just repeat that. I want to make this smaller than any given number epsilon, right? So if I just rearrange and bring the root 3 down here, then I know that if this is true, then I can get this less than epsilon. So the important thing here is that we're now going to choose or construct the delta from that definition. Now delta will normally depend on epsilon. So you're given some sort of epsilon and then you can choose your delta. What is it? Implies t sine t. Whew. Okay, that's a hard problem. Okay, can I have a show of hands? Who's seen something like that, maybe vaguely something like that before? Okay, who hasn't seen anything like that before? Really? Come on, be honest. Who hasn't? Like, it's important for me to know. Who hasn't seen anything like this before? Up the back? No, everyone. Okay, that's cool. I thought you wouldn't have seen anything like this before, because these sort of techniques are not really taught in first year for the functions, the real valued functions. Okay, now so that's a hard question. So let's just recap. My idea is to work with this and simplify and form some sort of inequality, and then relate it back to this. Okay? Questions? Questions? It's a challenging problem for, 9:15 in the morning. All right. If you can do these kind of problems, you have mastered limits, and I will bow down to you. So let's have a look at a problem and see how we can solve it just using the limits of the component function. So here's an example. Our vector valued function is defined in this way. For all t not equal to 0, calculate the limit of the vector valued function as t approaches 0. So how do we do it? Well, it's just a matter of taking the limits of each component function. Now the easiest one here is t squared. Then this one, and this one's a little bit harder. So
So the question is, what is this limit? Well, in first year or even at school, you learned that the limit is 1. Now, you can verify that with university techniques just by realizing that the limit of this component function here is a indeterminate form. If you take the limit of the top, you get 0. If you take the limit of the bottom, you get 0. And so, well, 0 over 0 isn't defined, so we need to work something else out. Well, under these conditions, and assuming the limit exists, we can apply L'Hopital's rule. So you differentiate the top, differentiate the bottom, and then retake the limit. So the derivative of sine is going to be cosine. The derivative of t is just going to be 1. Now, so you differentiate each part individually. It's not like you're applying the quotient rule here. And if I look now, well, the limit of the top is going to be 1, so the limit is just 1. So let's look at the limit of the other. So here I've used L'Hopital's rule. Again, that was learnt in first year. So the limit of the second component function, well, limit of the top is going to be cos of 0, so that's 1. Limit of the bottom is also going to be 1, so again I get 1. And the limit of the third component function is just 0. So let's put those components together and form our limit vector. Okay, so it's going to have these components. Now, a good realization there is you can use first year techniques on the component functions in here. So you already know lots of rules and methods and techniques for evaluating limits. Well, with limits of vector valued functions, you can just apply those techniques to the individual component functions. Let's move on to something else. Let's consider this vector valued function, and the limit this time as t approaches positive infinity. Okay. So let's consider the component functions. Now, what do you think the limit should be in this case? Well, the limit of the last one's probably this vector, the component here is easiest to evaluate. What's the limit of e to the minus t going to be as t goes to infinity? 0, right? So it's just the other two that we want to evaluate. So what do you think the limits of the other two are going to be? 0. Why? Yes? Yeah, yes, so that's sort of like the intuitive, like that's what's going on in our heads, but can you sort of give us some sort of theorem or proper technique? So you're right, but any ideas on how you might prove it or justify it, perhaps? No? Anyone? Anyone want to step in? Yeah, who said that? Yes, you rule too. Pinching theorem or the squeeze theorem or the sandwich theorem, depending on where you are in the world. So I'm just going to restrict the domain to, oh, hang on. Sorry, let me cover that up. Sine squared is between 0 and 1. If you divide, then you can have that, right? So
The pinching theorem or the sandwich theorem or the squeeze theorem, whatever you want to call it, says we can take limits, keep the inequalities, and if those, if we get equality, then we can say that the limit's going to be 0. So you put a limit here, a limit here, a limit here, limit here, limit here, limit here. On the right-hand side, you're going to get 0. So the thing in the middle has got to be greater than or equal to 0 and less than or equal to 0. Well, it's got to be 0 then. Sandwich. So we know the limit of this is going to be 0 as well. Okay. So again, this is just an illustration of applying first year techniques to the individual component functions. So you can do that. That's an important thing to recognise. Okay, any questions for that one? All right, well, limits and continuity. We know that continuity is an important thing. Now, I want to know why, though. Why are we interested in continuous functions? Why does it make a difference whether they're continuous or not? Why is it worth looking at continuity? Anyone remember from first year? Yes? Yeah, if a function's differentiable, then it's continuous. But we're not quite at differentiability or derivative yet. Why are continuous functions important? Come on. Why is it worth spending time wondering whether a function's continuous or not? Well, let me tell you. Continuous functions, no, you don't have your hand up. Continuous functions are predictable in some sense, right? Continuous functions don't just sort of move and then suddenly jump off somewhere else. They have a continuous sort of flow to them that we can predict. Now this I guess the property of continuous functions, or the continuity property, is used in lots and lots of theorems, okay? So it's a very powerful thing. If we know a function's continuous, then we know we can do things with it. If we know a function's differentiable, like you were saying before, we can do even more things with it, okay? So let's have a look at the definition of continuity. So a vector function is continuous at a point, say t0, in its domain, if the limit of the vector function equals the value of the vector function at t0. Okay, so going back to the previous definition, the limit big L is actually the value of the vector function at t0, r of t0. Okay, and we just sort of use the slang, we say a function's continuous, just continuous, if it's continuous at every point in this domain. Okay. All right, so an important concept there. Again, we can break it down to the component functions. A vector function will be continuous if and only if each of its functions in the components are continuous, right? Okay, let's have a look at an example. Briefly explain why the vector function given here is continuous. Who could briefly explain it to me? I've forgotten. without using any epsilons or deltas or anything like that. Yeah, yes. Absolutely, yes, you rule. What's your name? Yes, we have a deep, profound understanding, you and I. You can read my mind. I can see it in your eyes. Each component, is that what who else had, you had your hand up? No, you did. Is that what you're going to say as well? That's it. Each of the component functions are polynomials, right? T squared, t cubed, 1 minus t. All polynomials are continuous. Now, if you're not if you want to make a distinction, you can always say, instead of just saying R is continuous, you can just say R is continuous on the set of real numbers. I mean, in my opinion, it's good to say what sort of set you're talking about. Is it the whole of the domain, or just a point, or just a set of points? So that would be a perfectly reasonable answer to a question like that. You don't have to prove it. They're polynomial component functions. Okay. Now, here's another example. Consider the following vector valued function. This is just something that I've constructed. It doesn't necessarily have to have any physical meaning. What vector value can we define R of 1 to be? Notice that up here, this isn't defined for t equals 1. So how can we construct the vector value of R of 1 that will force this vector function to be continuous at t equals 1? Now, this is similar to, I guess, some of the problems from maybe 1-1-3-1. 1-2-3-1, but it's in a vector setting now. So can anyone suggest how we might tackle this problem? Yes.
The individual limits.
Yep.
Make them all the same, and then use that as the definition for R.
Yep. So let's take the limit as t approaches 1 of each component, right? And if they exist, let's make that the definition of R of 1. That's what you're saying, right? Yeah, good, thanks. So we want to force this to happen. Because if we know this happens, then we know R is continuous at t equals 1. So let's calculate the left-hand limit, and then we'll define this to be whatever's over here. Okay? We have the power to define R of 1. It's not defined, it's open, because the top definition doesn't include the point t equals 1. So we have the power to define R of 1. All right, so consider, please. Let's look at the limit of the first component function. What's this limit going to be? Well, if you try to evaluate it, it looks like it's going to be something like 0 on 0, right? Indeterminate form. Oh, the Hospital's rule, yes. So if we evaluate the limit of the top and the limit of the bottom, we'll get, again, I'm abusing sort of the mathematics here, we get 0 on 0, which is the indeterminate form, which we don't know how to evaluate we don't know how to determine it. You need to do some more digging. So let's apply the Hospital's rule. To apply the Hospital's rule, you differentiate the top, differentiate the bottom, and retake the limit. Now, you're making those differentiations independent of each other. It's not like the quotient rule or something like that. So
So the top's going to go to minus pi cos pi t, and the bottom's just going to go to 1. So using log.
So what's our limit going to be? Oh, sorry, positive. Yep. So what's our limit going to be? What's that limit there? Limit as t approaches 1 of pi cos pi t. Pi, right. Is it pi? Minus pi. See, I was right. I was putting in the minus sign a little too early. Okay. So what about the second one? Well, that's just the same story. You're going to get, again, I'm using the notation or the mathematics, you're going to get 0 over 0. Again, apply the Hopital's rule, but this time you're going to get, what do you think? Minus 2 pi. I'm not going to write down all the details for those. Again, you're just applying the Hopital's rule. Okay? So, sorry, say again? Oh, yeah. So sorry. So this limit's going to be, it's going to go to 2 cos 2 pi t, which is going to be 2 cos of 2 pi. So is that going to, that's going to be positive 2 pi. All right. I'm having a bad morning. So it's a good thing I apologised in advance for the mistakes I'm going to make. Okay, so what should we, assuming we can take our limits, what should we define r of 1 to be? Well, it's just going to be the vector with these components. All right. So assuming you can take your limits, not a very difficult question. Okay, well, what about we've already seen a limit that doesn't exist. Let's just explore that in a different way. So here's something that I just want you to consider. This isn't in your notes. You don't have to copy it down, but I'm just defining a vector function here. And it's one that we've seen before. So what would the curve of that, of the associated with that function be? How could you interpret that? Just in the plane. Circle, right, unit circle. And if t is the angle to the positive x-axis, then you're going to get something like this. Okay. Now we know that that's a circle because you can just look at the magnitude or the length of the vector function. You know it's going to be 1. And so, no matter where you are, you're always 1 unit away from the origin. So it's going to be a circle. Now, the question is, does the limit of r as t goes to infinity exist? And if so, what is it? So here's the question. So I want to think about that for a few seconds. What happens? I haven't sort of formally defined what we mean by a limit as t approaching infinity. You would have seen the sort of the basic case in first year, but we're dealing with vector functions now. So what does that mean? So anyone got any comments to make? Does the limit exist? No. Who said no? Okay. Why not? Just sort of. I mean, we haven't had any formal definition. Right. Now, what's going to happen as t increases? The thing just goes round and round and round and round and round. It doesn't approach a particular point on the, in the plane, right? So now geometrically, this thing's just going round and round and round, and it's not approaching any point in the plane. Huh? What's that?
The formal definition of the limit was the circle.
Yes, but we're talking as t approaches infinity now, right? Okay, so that's one thing. So I guess what I'm trying to do here is just give you some intuition without formally defining what we mean by a limit as t goes to infinity. Yeah, so you're thinking about a circle, yeah? So tell us more.
It's always put at the same distance from the zero vector.
Yes?
So therefore the limit as it approaches is the zero vector?
No, because, I mean, let me hang on, I'll get back to that in a second. Yes? Yes, that's good. I like that. So cosine t and sine t don't have limits as t goes to infinity because what do? They just go up and down they oscillate between -1 and +1, right? They never approach anything. So that's perfect. So this limit doesn't exist because the limits of the component functions don't exist, right? Another way of doing this is, okay, well, look at the curve. The curve is not approaching one single point as time goes on. Okay, it's just sort of repeating itself, just like a sine curve or a cosine curve. Well, you only need one of these limits of these functions not to exist for the whole limit not to exist, okay? So you don't need both of them. Need a component function. Okay, so let's say this was a cosine t and this was a 1, okay? The limit still wouldn't exist because the limit of that doesn't exist. Okay, so I'll leave it there. See if you can get some geometric understanding into that problem, and I'll see you all tomorrow.